Hello everyone and welcome to this podcast for genetics. In this podcast we're going to talk about complementation tests. Complementation tests are performed to determine if various mutations are found on the same or different genes. So to get a better understanding of when and how we're going to use this complementation test, let's use an example of a lab that's interested in learning more about tail development in mice. And so let's say they take this male mouse here, and let's say they feed this mouse a mutagen. It eats the mutagen, and now this mouse has gametes that have been mutated. And for this purpose, let's say this is a male mouse. So now you take this mutagenized mice, and now you're going to cross it with an unmutagenized female mouse. Now there's going to be a series of crosses, and we're not going to get into the different crosses that would have to be done. But ultimately what you're going to end up with are a series of mutants. Some of the mice are going to have mutants that we're interested in, those that don't have tails, for instance. Some of the mutants are going to be things we're not interested in. But since we're talking about tail length here, let's say that we get these 4 mutants that we're interested in. And we're interested in these 4 mutants because they lack tails. Everything else seems to be fine on them, but they do lack a tail. And let's label these mice as mutant A, B, C, and D. So now that we have our 4 mutant mice here, we now want to know which gene is mutated in these mice that causes it to not have a tail. So let's talk about that for a moment. And as we're talking about that, let's think about what we do and we don't know. We don't know how many genes are needed to make a tail. We also don't know if mutants A, B, C, and D have the same or different genes mutated. It's possible that the reason each of these mice lack a tail is because the exact same gene has been mutated. It's also possible that there is a different gene that is mutated in each of these mice. All we know is that we have 4 mutants. And because of the way the crosses were set up, that we know that these mutants have only one gene mutated in them that is linked to tail development. Alright, so how are we going to determine how many genes we're looking at here? How many different genes are represented in these 4 mutants? And that is when we're going to do the complementation test. So before we talk about our specific mutants here, let's consider 2 general rules of a complementation test. And they are that if you take a mutant times a mutant, and you get a restored wild-type phenotype, then 2 different genes are mutated. We would say that these 2 mutants complement each other. Now, the alternative is if we do this cross, take a mutant times another mutant of the same phenotype, and as a result, the progeny all have the same mutant phenotype, we say that these mutations are on the same gene, so one gene. We say they do not complement. So by doing a complementation test, we're going to cross these different mice, and we're going to determine if they are represented by one or multiple genes. So let's take our mutant A mouse, and we're going to cross it with our mutant B mouse. And in doing this cross, all of the mice that are born have no tails. In this case, we're going to conclude that mutant A and mutant B, so let's write this down. So mutant A and mutant B have a mutation in the same gene. When we did that original mutagenesis, it mutated the exact same gene. And so we say that A and B do not complement each other. What I'd like to do now is think about what that gene might look like to help understand why the progeny still don't have a tail. Let's say that we have these 2 chromosomes. And in this chromosome, we have a gene here. Well, I'm going to give it a couple genes. We're going to call this gene 1, gene 1, gene 2, gene 2. And let's say, just for the sake of argument, that to make a tail, you need both gene 1 and gene 2. But in our mutagenic studies, what happened was that we generated a mutation in gene 1. So I'm going to make a little X here in gene 1. And so that's why our mouse 1A here, the mutant A, doesn't have a tail, because it doesn't have a functional gene 1. Its gene 2 is fine, but without 1, it can't make a tail. Now, mutant B here was also a result of a mutation in gene 1. Now, it's unlikely it's going to be the exact same mutation, so I'm just trying to intentionally put it on the opposite end of the gene. So why is it when these two mice mate that the progeny don't have a tail? Well, let's think about what the gametes look like. Each of these are going to make haploid gametes, so they're going to have one copy of gene 1 and one copy of gene 2 in them. And because the parents each had gene 1 mutated in them, in the gametes, they're also going to be mutated in gene 1. When they fertilize each other, to make the fertilized zygote, it's going to take this set of gene 1 and 2 from mutant A, and then it's going to take this gene 1 and gene 2 from mutant B. And as you see here, this progeny resulting from A and B lacks a functional gene 1, and so no tails. So we can conclude, as I said earlier, that mutants A and B each have a mutation in them necessary for tail development, and the gene that's mutated in each of these is the same gene. In this example, it's gene 1. Well, let's cross mutants C and D now. Okay, so now let's consider mutant C and D, and let's see what happens when we make those two together. Turns out when we make C and D together, we make progeny mice that all have a tail. From our rules, we know that if we take two mutants and when we mate them, the progeny are all restored to wild type. We say then that mutant C and D have mutations in different genes. We say that these mutations, so these two mutations, complement each other. So let's look at the genes in mutant C and D to see if this makes sense. So let's say that in mutant C, gene 1 is mutated. And so in mutant C, we don't have a functional gene 1, so you don't have a tail. Since they're going to complement each other and they're going to be separate genes, mutant D is going to have a different gene mutated. Mutant D maybe has gene 2 mutated. How does this now go on to make a baby with a tail? Let's now go back and look at the gametes that are made from mutant C and D. Mutant C will make a gamete that contains gene 1 and gene 2. Gene 1 is going to be mutated. Gene 2 is not mutated. Mutant D will make a gamete, but in this case, gene 1 is fine, but gene 2 is mutated. Now, when these gametes come together to create the fertilized zygote, it's going to take these two chromosomes and bring them together. Now, remember, this chromosome here is coming from mutant C, and so gene 1 is mutated. This bottom chromosome here is coming from mutant D, and so gene 2 is mutated. As you can see in this zygote here, that's going to ultimately become this mouse here. It has one functional copy of gene 1, which it gets from mutant D, and it has one functional copy of gene 2, which it gets from mutant C. We say then that mutant C and mutant D complement each other because they are able to add the necessary genes to restore the phenotype. In this case, to restore the wild-type phenotype of having a tail. Because different genes are mutated, they will produce gametes that have different genes that have the mutation on it. When they form the fertilized zygote, they're able to have one functional copy of each of the genes necessary to make a mouse here that has a tail. For now, that is all I have to say about complementation tests. We'll talk a little bit about it in class, and I'll definitely have a question on the exam about complementation tests. So if you have any questions at all, please make sure you come see me. If not, I will see you in class. Bye.